Okay, let's get back to this question of sort of how big an eigenspace is, how many vectors, how many eigenvectors you need to span it. Recall that in the last section we defined the algebraic multiplicity of an eigenvalue of a matrix A to be the number of times the corresponding linear factor occurs in the factorization of the characteristic polynomial of A. Okay. So to find the eigenvalues, you factor this characteristic polynomial, and if a certain factor occurs more than once, then that, that adds to the algebraic multiplicity of that eigenvalue. Okay, the geometric multiplicity of an eigenvalue is just the dimension of the lambda eigenspace. And so, it's the number of sort of independent eigenvectors you have for that eigenvalue. Okay, so let's show real quick that we have this nice formula for the geometric multiplicity. Right, why is this? Well, so the geometric multiplicity of lambda is, by definition, right up here, dimension of E sub lambda, right? And we showed on the previous page that E sub lambda is the kernel of A minus lambda in. Dimension of the kernel, and blast from the past, that's the nullity, right? It's the nullity of that matrix. And we've got this great sort of fundamental theorem of linear algebra called the rank nullity theorem, which says that the rank and the nullity always add up to n. We have a square matrix here, so I don't have to worry about whether it's which dimension it is. It's n. And so that means that the nullity is n minus the rank. Right? And remember, the rank is the dimension of the image, but well, this is a nice form. Okay, so that's exactly what you see up here. So, all right, what does this mean in practice? Well, you could look back at the first page actually and see how it plays out, but just for variety's sake, let's look at another example. So here's a matrix and happens to have eigenvalues 0 and 1. So let's figure out what the geometric multiplicities of those eigenvalues are. So the geometric multiplicity of 0, by definition, is the dimension of E0, which is the dimension of the kernel of this matrix. Okay, but I don't need to write all this. I'm supposed to be using this formula up here, right? So, so ignore that. So far, it's just the n, which is the dimension of your matrix, right? 3 minus the rank of A minus 0 I in this case, right? So this matrix A. And well, remember, the one way to think about the rank is it's the number of linearly independent columns, right? It's also the number of ones in the reduced echelon form, if that's helpful. If you look at this thing, then clearly the second column is redundant because it's a zero vector, and the first and third are independent because they're not scalar multiples of each other. So the rank of this matrix is 2, and therefore we have an answer of 3 minus 2 equals 1, right? The rank is 2, therefore the nullity has to be 1. Right? Therefore the kernel of this matrix, which is the eigenspace, is spanned by one vector. Okay, so in fact, we know what that vector is, right? It's just 0, 1, 0. That's the combination of these columns that would give you the 0 vector. So the eigenspace E0 is actually the span of just that vector, right? And that's enough. That's the whole eigenspace. Okay, so what about the one eigenspace? Okay, so let's think about dimension of E sub 1 now. Okay, jumping right to this formula, that's supposed to be 3 minus the rank of a minus 1 times in. So I'm just going to subtract 1 from the main diagonal of my matrix. So I get 0, 0, 0, negative 5, negative 1, 2, and 0, 0, 1. Uh-oh. Not 1. Let's see if we can fix that. Okay, 0, 0, 0. All right. So we killed these two ones, and now the only non-zero stuff is on the second row, right? So in particular, all three columns are scalar multiples of each other. And, well, for example, you could say the second and third columns are redundant, okay? So the rank of this matrix is just 1. And therefore its nullity is 3 minus 1, or 2, okay? So the geometric multiplicity of eigenvalue 1 is 2 in this case. And that means that the eigenspace E1 should be spanned by 2 vectors, right? A basis of 2 vectors. And let's see, can we guess those? Well, okay, we put a 1 right, for the redundant vector, and then what do I need to, zeros to the right of it, and what do I need to put here? So I have a negative 1 there. That'll make my life easier. Let me actually put a 5 here, so I have negative 5, and then get a positive 5 here, and that'll do it. Okay, so negative 1, 5, 0 is in the kernel of this matrix. And let's see, what if I take 1 of the last column and 2 of the second column and 0 of the first one? I think that would that linear combination would also give me 0. Okay, that's another linear relation, so it's a vector in the kernel of the matrix. Okay, so there we go. And this matrix would be diagonalizable, right? Because I have 1, 2, 3 linearly independent eigenvectors. So that they form a basis for R3. Okay, so I have an eigenbasis, so it's diagonal. The matrix A is diagonalizable. All right, here's one more to try. And if I were there with you in the classroom right now, then I would let you try this one on your own. So maybe pause the video and give it a try, and fire it back up when you're ready. But I'll go right ahead. So let's see. E0. Well, if we're going to use the formula above, then the let's see, what am I trying to say? Let's just go ahead and find the eigenspaces. That's more fun anyway. So this is going to be the kernel of A minus 0 times identity, so just of A. I'll copy it here. Okay. And so let's see if we can. All right, so what's the rank of this matrix? It's 2, right? The first 2 columns are independent, but then the third one is equal to the first one, so it's redundant. So, okay, if the rank is 2, then the nullity is 1, so we're going to find one vector in the kernel. And so we need a linear combination of these columns equal to 0, and I can do, for example, 1, 0, negative 1. So that single vector forms a basis for my kernel, and therefore a basis for this eigenspace, E0. Similarly, E1 is going to be the kernel of A minus 1 times identity. So I need to subtract 1 from the main diagonal. And I get 0, 0, 1, 1, 0, 1, and 1, 0, 0. And, well, this time the first and third columns are independent, and the second column, being the 0 vector, is redundant. So I have a linear relation with coefficients 0, 1, 0, and that tells me that this one-dimensional kernel is spanned by the single vector 0, 1, 0. All right. And finally, the 2 eigenspace, E sub 2, going to be the kernel of A minus 2 times identity, so I subtract 2 from the main diagonal, which will give me a negative 1, 0, 1, 1, negative 1, 1, and 1, 0, negative 1. And this is a little bit trickier. The first two columns are definitely independent. Turns out the third one is a linear combination of the first two. It is redundant. So we again have a rank of 2 and therefore a nullity of 1. So it's going to be one vector in the basis of our kernel. And I suppose if I want to get the opposite of this vector, so I need to get negative 1, negative 1, 1, I could take one of these and then 2 of those, right? So if you take that linear combination, you get 0, so that's a linear relation. Therefore, it gives you a vector in the kernel, so the kernel is the span of that vector. 1, 2, 1. All right, and yet again, we have 3 independent eigenvectors, which form basis for R3. Therefore, this matrix A has an eigenbasis and is diagonalizable. By the way, I think I forgot to point it out, but did we have any examples yet that were not diagonalizable? No, I'm confused. Maybe all of them were. Okay. All right. Well, that brings us to the question. When can we find enough eigenvectors in the eigenspaces to form an eigenbasis, right? Up here, we only had 2 eigenvalues, 0 and 1, but 1 contributed a couple independent eigenvectors. So we still got 3 independent eigenvectors altogether. In number 5 here, we had 3 different eigenspaces, and they each contributed 1 eigenvector. And they all happen to be independent, right? So, is this always going to happen? Or how can we tell if we're going to get enough eigenvectors to form an eigenbasis? All right. Well, think about this example. Suppose we have some n by n matrix of some size with eigenvalues negative 1, 2, and 5. And, okay, so we have corresponding eigenspaces, E negative 1, E2, and E5. And those 3 subspaces of Rn have these bases, okay? So we have a geometric multiplicity of 3 for negative 1, 2 has a geometric multiplicity of 1, and 5 has a geometric multiplicity of 2. Now, we know that, because these 3 vectors form a basis for that eigenspace, part of being a basis is that they're linearly independent, right? So in and of themselves, the u's are independent, and the v is independent, and the w's are independent. But what if we throw them all together? Is it still a linearly independent collection? Right? We know that, excuse me. Okay, I'm going to pause for a bit and start up again.